This is part 2 for section 9.3, so we're dealing with significance tests for means, and we're going to talk about two-sided tests. So at this Hawaii pineapple company, managers are interested in the sizes in pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. But a new irrigation system was installed in the field after the growing season, and managers are wondering whether this change will affect the mean weight of future pineapples grown in the field. So to find out, they do what every good statistician should. They select and weigh a random sample of 50 pineapples from this year's crop. The Minitab output below summarizes the data. We've got to determine first whether there are any outliers. Ooh, outliers, good. I know we all have that memorized. All good to go, no problem. Yeah, so go ahead. Yeah, go now. Or I'll remind you. Either way. But just to make sure you know what all this stuff is that is showing, the N at the beginning is 50, which is our sample size. We have our mean from that sample. Our standard error mean, don't worry about that piece of data right now, I don't need it. Then we have the standard deviation, the minimum, the Q1, the median, the Q3, and the maximum. So to find outliers officially, we've got to use the IQR, the interquartile range, which is found by doing Q3 minus Q1. Remember, Q3 is the 75th percentile, Q1 is the 25th percentile, and the median is right in the middle, it's the 50th percentile. So we get an IQR of 4.125, and then any data that's greater than Q3 plus 1.5 times IQR or less than Q1 minus 1.5 IQR is considered an outlier. So you literally just plug the numbers into those two equations, and that gives you your mark where outliers begin. So we can do Q3 plus 1.5 IQR and get 40.30, Q1 minus 1.5 IQR and get 23.08. So anything higher than 40.3 is an outlier. Anything lower than 23.08 is an outlier. But you can see right there the minimum and the maximum. They are within that range. They're between 23 and 40. So there are no outliers. Excellent. That helps us know we can move forward. No outliers. All right. So let's go ahead and do this test. We want to test the hypothesis. The null hypothesis being that mu is equal to 31. In other words, no change, no difference from last year. The alternative hypothesis, if you look back, it just said they wonder if it has affected it or will make it change. They don't specify what direction, just that it changes. So we're doing a two-sided test, shocking, since that's the title of the slide, of mu does not equal 31. And we define mu as the mean weight in ounces, it's good to specify what units you're using, of all pineapples grown in the field this year. Since no significance level is given, we'll use oldie faithful. That didn't come out right. We'll use the one we always use, alpha equals 0.05. Plan. If the conditions are met, we should do a one sample t-test for mu. So now let's check those conditions. Random, we're good. We were told the 50 were a random sample. Normal, we don't know if the population distribution is normal, but since our sample size is bigger than or equal to 30, that tells us we are okay to use T procedures. And independent. There need to be at least 10 times 50 equals 500 pineapples in the field, because they were sampling without replacement. So we could expect many more than 500 pineapples in what they describe as a large field. You consider that this is a place that grows pineapples, so a large field seems reasonable to assume it would have more than 500 pineapples. So our conditions are met, we can move forward. So we do by starting with the sample mean and the sample standard deviation, and then we'll find our test statistic. We get 2.762 for our t. Now we need to do our p-value, You can use the calculator with the t-test to make this happen if you want. You can use TCDF, or you can use our favorite, Table B. And with Table B that is shown up here, since 49 degrees of freedom, we would go down to 40. We have to go to the one that is just below it. We see that it's going to be between 0.005 and 0.0025. But remember, this is a two-sided test, so we're going to have to double those two p-values to be between 0.0. Oh, so shouldn't they? Oh yeah, sorry, they did double. All right. So just make sure I'm saying it correctly. Table B shows it between 0.005 and 0.0025. So we double those, and the desired p-value is between 0.01 and 0.005. That shows us, as our conclusion, the p-value is clearly less than our alpha equals 0.05 significance level. So we have enough evidence to reject the null, so we've spoken about the null hypothesis there, and conclude that the mean weight of the pineapples in this year's crop is not 31 ounces, meaning we conclude that the alternative hypothesis is true. So we reject the null and accept the alternative hypothesis, but make sure when talking about the alternative hypothesis you talk about it in context. They don't just say conclude to agree with the alternative hypothesis. They say conclude that the mean weight of the pineapples in this year's crop is not 31 ounces. I want to relate these two-sided tests to confidence intervals once again. So this Minitab output is looking at the pineapple data, and they've already created the confidence interval for us. You can see it, it's right under 95% CI. The confidence interval is 31.255 to 32.616. So we are 95% confident that this interval captures the true mean weight mu of this year's pineapple crop. Given that 31 is not in there, we would say it doesn't seem likely that 31 could be the mean weight still. It seems likely that there is a change. So that's what the confidence interval would tell us. Because just like with proportions, there's a link between the two-sided test at significance level alpha and a 100 times 1 minus alpha % confidence interval for a population mean mu. I know those numbers may not seem perfectly natural here, but it's just the idea of a significance level of 5% would correspond with a 95% confidence interval, or a significance level of 10% would correspond with a 90% confidence interval. So for the pineapples, the two-sided test rejected the null, as we saw in the previous slide, and said there was sufficient evidence for the alternative hypothesis that the mean was not 31. And the corresponding 95% confidence interval does not include 31 as a plausible value of the parameter mu. In other words, the test and the interval both lead to the same conclusion of rejecting the null hypothesis. But, as we talked about earlier as well, the confidence interval really gives much more information because it provides a plausible set of values for the population mean, whereas the significance test really just told us it's not 31. Well, that could be true if it's really 29, or it could be true if it's 20, or it could be true if it's 40 or 50. And we really don't know with the null hypothesis, with the significance test, but the confidence interval tells us we're pretty certain the true mean is somewhere between 31.25 and 32.616. So there is more information we can gather from the confidence interval in that way. Then the connection between these two is actually a little stronger with means, because if you recall with the proportions we had an issue of one of them using p hat and one of them using p naught, but there's not a difference here because they both use the sample standard deviation. They both use Sx over the square root of n for their standard deviation, so that allows them to be much more similar. So it turns out, looking at what's in blue, when the two-sided significance test at level alpha rejects the null hypothesis, the corresponding confidence interval for mu will not contain the hypothesized value. So if the significance test rejects the null, then the confidence interval that's corresponding as far as percentage will not contain mu naught. But the flip side is, if the significance test, two-sided significance test, fails to reject the null hypothesis, then the confidence interval for mu will contain mu naught. Okay, we often are going to want to compare. That's often what they do in statistics because they're wanting to know how does the old compare to the new, things like that. So paired data. Comparative studies are often more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals result in paired data. When paired data results from measuring the same quantitative variable twice, as in job satisfaction survey. So that could be saying, how satisfied are you, and asking someone 1 month after they're in the job, and then asking them 1 year after they're in the job. So same person, same question, but different times. But we can make comparisons by analyzing the difference in each pair. So we actually, instead of just looking at them saying an 8 out of 10 and a 7 out of 10, we would subtract them and say 8 minus 7 and look at how the difference went down 1 or up 1 depending on which one was first. So then we call it the mean difference, mu d. So these are called paired t procedures. So let's do an example of this. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Man, that probably means no chocolate. Oof. During one 2-day period, subjects took capsules containing the normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo is randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. And just reminding us, if they're doing this experiment well, it was random as to which one someone got first, and it was also random, or it was also hidden from the subjects to know whether they were on the placebo or the caffeine. We'll do our state. Our null hypothesis would be that there's no difference, meaning mu d is 0. And the alternative hypothesis would be that the mu d is greater than 0, meaning that the depression increases when you have the placebo. So depression level with placebo is bigger than when you have the caffeine. And we'll do a significance level of 0.05. Let's plan. If conditions are met, we should do a paired t-test for mu d. The conditions are still the same, random, normal. We do have to look at the data here because the sample size is so small. Okay, this isn't super normal, honestly. You can tell we kind of got, it looks like 2 peaks in the histogram, and the box plot shows some right skewedness, but no outliers. But the normal probability plot looks fairly linear. So it's certainly not real close, but there's no strong skewness, and there's no outliers at all that we can see. So we decide t procedures are going to be close enough. We aren't sampling. We actually picked these 11, so it isn't necessary to check the 10% condition. And we'll assume the changes for the subjects are independent. In other words, how one feeling is not affecting how the other's feeling. So that was probably a good reason to make sure they keep these subjects separate. Then we have the mean difference from the sample and the mean standard deviation from the sample. We find our t-statistic and do our p-value. So we get a p-value that's very small, 0.0027. So we conclude, since the p-value is much less than our chosen alpha equals 0.05, we have convincing evidence to reject the null hypothesis that the difference is zero. We can therefore conclude that depriving these caffeine-dependent subjects of caffeine caused an average increase in depression scores. So we spoke both to the null, which we rejected, and the alternative hypothesis in context we accepted. So there's good evidence for it. I'm going to go through this quickly. I'm not going to read everything, but there are some important things in using tests wisely. So carrying out a significance test is often quite simple if you use a calculator or computer. I mean, we know how to do it with the t-test, but using it wisely, that can be a little trickier. So first of all, statistical significance versus practical importance. When a null hypothesis of no difference can be rejected at the usual levels, there is good evidence of a difference, but that difference may be very small. It could just be that it's 3% different, and when large samples are available, even tiny deviations from the null hypothesis will be significant. So we have to consider not only whether we we reject or fail to reject, but how big is the difference we're talking about. Because we may not care if it's a difference of 3%, but we would care if it was 10. Don't ignore lack of significance. There's a tendency to infer that there is no difference whenever a p-value fails to attain the usual 5% standard. But in some areas of research, small differences that are detectable only with a large sample size can be of great practical significance. So in planning a study, verify that the test you plan to use has a high probability or high power of detecting a difference of the size you hope to find. So it's important to look at how important the difference is. When we're talking about how much vitamin C stays in someone when they take a vitamin, that's important, but frankly it's not as important as how much fuel is going to be used when they're shooting off a space shuttle. That's something they've got to make sure they do a little more carefully. I don't know if those are great examples for significance tests, but I hope you see it's important to look at the level of importance as far as how close we are. And statistical inference is not valid for all sets of data. If we have badly designed surveys or experiments, that can produce invalid results. So inference cannot correct flaws in the design. Each test is valid only to certain circumstances with properly produced data. So if we do poor sampling or poor experiments, the math being strong doesn't help because the numbers we're plugging in are poor. And beware of multiple analysis. Statistical significance ought to mean that you have found a difference that you are looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking beforehand, then design a study to search for it, and then use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. So it has to be something where you're trying to find something specific and then you test that way. Alright, that completes section 9.3. I wish you all the best.